Monday, and so on Friday we'll just be doing review. So come with questions. Try to take a look at those old exams and see where you think you are the weakest. We're picking up in Chapter 5. We did a little bit of Chapter 5 on the previous exam, just cross product and a couple of basic right-hand rule stuff. But we'll have more right-hand rule. We'll have mass spectrometer. You'll have everything past sort of the first couple pages in Chapter 5. All right? And then Chapter 6. And then this portion of Chapter 7, leaving out AC circuits and phasers. So if you see that in the homework or the old tests, you're not going to see that on the exam. More about that before the end of class. All right, so let's look at an LC circuit. I want to know its maximum current. The LC circuit has a 1.5 microfarad capacitor. That's our C, right? Capacitance. And then it has an inductor, which is 12 millihenries. And that's all we got. So the capacitor had previously been charged up by a 12-volt battery. All right, so you use a 12-volt battery, charge up this capacitor, and then that gives you a certain amount of charge. I mean, you probably know how much charge it gives you. It gives you Q is equal to C times V, so 1.5 times 12. So you have 18 microcoulombs of charge. Now what's going to happen now as we go through this is that we will see that charge, that 18 microcoulombs of charge, is going to go out through the circuit, and then it'll come back. It'll oscillate back and forth, back and forth. And we developed that expression for the back and forth of their energies between the electric field and the capacitor and the magnetic field and the inductor. Listen, you need to sort of have a basic understanding of these three circuits, RL, LC, and RLC circuits, be able to draw their voltage curves with respect to time, and be able to just describe in words what's going on with them, how the inductor impedes the current as it's increasing, and sort of keeps the current as it's decreasing, and how this circuit switches back and forth. You might have a short answer that just says, describe what happens in these circuits with time, or sketch out the graphs for the voltage and or the current as it goes through time. All right, so be able to describe these three circuits that we've been doing, the RL, the LC, and the RLC circuits. All right, so first of all, what is the maximum current? I want to know what is the maximum current. We assume that the circuit loses no energy. So this is an assumption that we have. And behind that assumption is another assumption. If our circuit was losing energy, what would that tell you about the circuit? Or what would be required for us to lose energy in this circuit? What type of element would I have to have in the circuit? What type of device would have to be in the circuit in order to actually lose energy? Where that electrical energy would be turned into thermal energy. A resistor, right. So if I have a resistor, then it's going to lose energy. So what we're saying is when we say that the circuit loses energy, or loses no energy, is that there's no resistor. That's not entirely true because, the wires have some resistance, the inductor has some resistance as well. So that's not entirely true. We sort of talk about this energy swapping back and forth forever, but that doesn't happen because there is a certain amount of resistance in the circuit, and eventually you're going to lose all of the energy in the circuit as that current travels through the wire. All right, so first I want to know the maximum current. The maximum current occurs when UV is at its max. And remember, UV, that's the potential energy in the magnetic field. That occurs here. I get that maximum potential energy in the magnetic field when the current is at its maximum value. And we have this expression that we found for UV is equal to 1/2 Li squared. So when UV is equal to its maximum value, that's when the current is at its maximum value. But I know that the maximum magnetic energy is equal to the maximum electric energy. And if you recall, the electric field energy is in the capacitor. And the maximum electric field energy, the maximum potential energy in the electric field, occurs when I have maximum charge on the capacitor. Remember, I have all my charges here. That means that I have the most electric field lines and the most energy, the strongest electric field inside my capacitor. So I have a couple things. I want to know what is the current when this is at its maximum, but the value for this that is at its maximum is equal to the value for the electric field energy, right? Because they swap back and forth. Now when this is at its maximum, this is equal to what? It's equal to 0, right? All the energy from the electric field is transferred over into the magnetic field. But they both have the same maximum value because there's a certain amount of energy in the circuit, and that doesn't change with time. So what I'm going to do is I'll say 1/2 Li squared is equal to 1/2 Q squared over C. Because this is my electric field energy, UE is equal to 1/2 Q squared over C. Or, we had different expressions for that. You could say C times V squared, or but this is the easier way to do it. And then I'll solve that for I. If I solve it for I, see these cancel out. I solve for I, it's going to be the square root of Q squared over LC. Remembering that Q is equal to C times V. That was 1.5 microfarads times 12 volts. That's equal to 18 microcoulombs. Or I'll need to change this to 18 times 10 to the minus 6 coulombs. All right, to keep with SI units. So what I get here is I get the square root of 18 times 10 to the minus 6 coulombs. That's the maximum charge on the capacitor, squared, divided by my capacitance and my inductance. And let's see, on our circuit, our inductance was 12 times 10 to the minus 3, because we want it in henries, not millihenries. That's the SI unit. And then the capacitance was 1.5 times 10 to the minus 6. That's in farads. All right, and that gives us our maximum current, which is going to be 0.13 amps. So if I look at my current versus time, my current is going to, the current in the inductor, if I start with my capacitor fully charged, my current starts at 0. Your current is going to oscillate back and forth, and it's going to oscillate between plus 0.13 amps and minus 0.13 amps. And we're sort of getting a little bit into alternating current here. In fact, inductors are these LC circuits are very important with the idea of alternating current electricity. Use this idea to make our current go back and forth. All right. You have some more homework questions that are similar to this, but you'll need to be able to solve for this maximum current, and then also be able to describe how the current changes with time and how the energy is switched back and forth, like we did last time in class with the LC circuits. Let's look now at damped oscillations. Are we clear with this though so far? Stick to your homework. Like, make sure that you can do your homework for this chapter. Your exam will look a lot like your homework. It's not going to be identical to it, but it'll be very similar. And then, as I said, be able to describe in words these different circuits and how they operate. what they do, be able to sketch out the graphs for the different quantities, the current, the voltage, the energy with respect to time, how that differs with time. Okay? Don't forget, too, that there's a take-home. I gave it to you last time. I just want you to show me that that solution that I gave you is a valid solution to the second-order differential equation. It's really just a matter of taking the derivative of your cosine function a couple of times. I'll send that out on Moodle soon, in the next day or so you'll have it more formalized. And since our exam is on Monday, if you turn it in on Monday, that's fine to take home, but if you want to wait until Wednesday, that's fine. I know that it's a busy week for y'all. Okay? So you can push your take-home back for Wednesday. But I'll need to have it by Wednesday just so I can get that credit assigned to your exam. Okay, let's look at damped oscillations. You know, we've been looking at these. We saw that in a RL circuit that my current with respect to time, or my voltage with respect to time, it looked like this. It decayed over time, very much like it did with the RC circuit. And then we saw with the LC circuit that the current with respect to time looked like this. And now we'll see that with an RLC circuit, that now we have this resistive element so that our energy is actually going to decay over time. What we're going to see is that our function will look, it'll look like this. So that you have this sine function overlaid onto an exponential decay curve. All right, so the sine function will decay over time. And so we have this sort of progression in these three different circuits as we add these different elements. The RL, which acts just like the RC circuit, the LC, which oscillates back and forth, trading that energy between the electric and the magnetic fields, and now the RLC circuit, where we'll still trade that energy, but we'll gradually, or we'll exponentially lose energy as time goes on. And so our current will decay over time. This is current versus time. All right, so the LC circuit loses no energy. As we said, because it has no resistor in it. But if the circuit has a resistor, it dissipates energy. I mean, that's what resistors do. They dissipate energy. And they dissipate it at a particular rate, right? That power rate, the power is VI, or the power is V squared over R. So we can figure out how much energy it loses. But an LRC circuit will lose energy over time because I have a current going through it. And that current produces thermal energy, which is lost energy in the circuit. So my total stored energy in my circuit, U total, is going to equal to the magnetic energy plus the electric energy, the electric field energy. And those are two things that we've seen already. We have 1/2 Li squared plus 1/2 Q squared over C. Those are going to change with time, but there will be a total stored energy that will decrease over time. This decreases at the rate of power. Our du dt is going to be equal to negative I squared R. And remember, I changes with time. And so we can create, if I have this current, which is actually going to change with time, so I can create this second order differential equation, an ordinary differential equation. That just means it doesn't have partial derivatives, it just has regular derivatives in it. So I get this, I get du dt is going to equal to Li di dt plus q over c dq dt. And this is all going to equal to the negative I squared over r. All right, negative I squared r. That the total amount of energy is equal to the rate that, or the change in energy rather, is equal to the rate at which I lose energy. In the past, I've done this as a take-home. Like I gave y'all the easier of the second order differential equations to solve. And so in the past, I've done this differential equation to solve. It's not terribly important for you to understand how we get this equation, so don't sweat this too much. It's just in the past I've given the other students this equation to show as a take-home. But I gave y'all the easier one because, I don't know, just because I just did. But anyway, so this di dt is equal to the second derivative of q dt. Now, because remember, I is equal to dq dt. And so the second derivative of that, or the derivative of current, is the second derivative of the charge with respect to time. Let me step back through that again. Let's make sure that's clear. The current, I, forgetting the d here, is equal to dq dt. Q over t. That's how we define current. The rate of the flow of current or of charge with respect to time. So that's dq dt. And then we take the derivative of it again, and that gives us the second derivative. So this di dt here is equal to d squared q dt squared. And so now I have this this differential equation which looks like this. I have L dq dt, that's from here, d squared q dt squared, plus r, I just take this over here, and then that's where it becomes here, plus r dq dt dq dt. That's the I squared right here. It's just dq dt squared. I'm writing them out because one of these dq dt's is going to cancel out. Plus 1 over c times q dq dt. That's this thing right here. And this is all equal to 0. And so my second order differential equation, I can cancel out some things and get rid of this, this, and this just by dividing the whole thing through. And I get this second order differential equation. L d squared q dt squared plus r dq dt plus 1 over c q. And that's all equal to 0. The solution for this, we had an equation before that was missing this part right here, and we found that the solution to that was either a cosine or a sine function, and that's part of your take-home. But the solution in this one is actually going to be a damped oscillator, and the solution will look like this. It'll be Q, this is our solution, is that Q is equal to the maximum charge times e to the minus RT over 2L times the cosine of omega t, actually omega prime t, plus phi. This is on your equation sheet, so don't sweat memorizing it, and don't even really sweat the second order equation because it's not going to come back to you on the exam. But you will need to use this expression in order to solve for the charge at particular times in our RLC circuit. It's on your equation sheet, so don't bother memorizing it, but you will need to know how to use it. We need to define these frequencies, this omega and omega prime. We've already defined omega. We defined that in the previous second order equation we saw, and that's that 1 over square root of LC. Omega prime here listen, if you go into differential equations, which some of you will, you'll figure out how to determine these omegas. You'll see some of it when you do the take-home, how that omega figures into how you determine the solution. But my omega prime is equal to omega squared minus r over 2l squared. Y'all do stuff like this in DE, Josh? You don't, oh, you had it.
We in the plot transformation right now.
Oh, okay.
It's nightmare time.
Yeah, I hated that class. It was not fun. There's not really that much in the class that you'll actually need in the future. But differential equations are important. Like whenever you have something that changes with time, they can help you to predict how that quantity will react in the future. So anytime you have multiple variables that are changing with time, as is often the case, you chemists and you engineers, it's important to know how to be able to solve those equations. So anyway, that's our solution to that second order differential equation. As I said, it's on your equation sheet, so don't bother memorizing it. But the function for this looks like this. I've already drawn it, but if I plot Q versus T, and your current's going to look the same. See, cosine of 0 is 1, right? So it's going to start up here, and it'll go like this. Because I got the cosine function, and that causes it to oscillate, but then I also have this exponential decay function, and so that causes it to decay with time. Alrighty. Let's do a sample problem, and you have some in your homework as well. So let's look at a circuit. I have a capacitor, I have a resistor, and I have an inductor. The capacitor is 1.6 microfarads, the resistor is 1.5 ohms, and the inductor is 12 millihenries. And I want to know a couple of things. I want to know the time when the charge on the capacitor is 1/2 of its maximum charge, how many oscillations have occurred in that time, and I want you to sketch a plot of U versus T. All right, so let's look at the first one. First of all, I know that Q is equal to my maximum charge times e to the minus RT over 2L. This is just my solution to that ODE, that ordinary differential equation, times the cosine of omega prime t. We haven't really talked about phase, about the phase, that phi that we had before, but we'll just always assume that phi is equal to 0. It has to do with the shifting of your cosine or your sine function. So we'll always assume that our phase, that phi variable is equal to 0. All right, so Q is equal to that expression. We want to know when Q is equal to 0.5 of my maximum Q. Right, that's my maximum value. So we say, first of all, that my cosine omega t term is going to have to be equal to 1 in order to find that point where Q is equal to 0.5 Q, right? Half the maximum value. So we'll have 0.5 Q is equal to Q times e to the minus RT over 2L. My Q's are going to cancel out. And then I can solve this for T. So I get the natural log of 0.5 is equal to negative RT over 2L. That's going to be 1.5 T divided by 2 times L, which is 12 times 10 to the minus 3. All right, and then I solve that for T. And I find that T is equal to 0.011 seconds. All right, just it's the natural log of 0.5 times this quantity divided by this quantity. This turns out to be negative, so it drops the negative in that equation. All right, so that's how to find when my charge is at 1/2 the total charge. You could also conceive of, if I gave you what is that total charge, that you could find the particular time that it is, find the charge at a particular time as well. Now I also want to know how many oscillations occur in this time. In order to do that, I need to think about my frequency. Now we define the angular frequency. The angular frequency with this omega equals 2 pi f. We call this the angular frequency. It's the same as the frequency that we have. The omega was the square root of 1 over LC. So this omega is the same as we had before, where omega is 1 over root LC. That came up in our differential equation. So that's called our angular frequency, that omega, that 2 pi times f. And if I want to know the period, you know how period and frequencies are related? Right, frequency is a per second, and so a frequency is just the inverse of the period. So my frequency is 1 over the period. And what I want to know is, what is this period? Like, what is the time for one oscillation? This is called the period. That's the time for one oscillation. And so if I can find the time for one oscillation, then I can figure out how many oscillations have occurred at 0.011 seconds, just by dividing 0.011 by the period t. So I can go about this by finding first what is omega. It's this 1 over the root of LC. That's 1 over the root of 12 millihenries. 12 times 10 to the minus 3 henries times C, which is 1.6 times 10 to the minus 6 farads. And I get an omega. Let's see, what do I get for that? Well, I don't have that written down. I get 7.22 times 10 to the third. All right, 7220. That's the angular frequency. It's not, it's like in radians per second. It's not have to do with an actual frequency or 1 over seconds. All right, so now I want to know the actual frequency. So omega is equal to 2 pi times f. So frequency then is omega over 2 pi. And I get 1.15 times 10 to the third. That's in hertz. So that tells me the frequency, that is 1 over seconds for that particular oscillation. And now to find the period, it's going to be 1 over the frequency. So just take the inverse of that, and I get 8.7 times 10 to the minus 4 seconds. This is the time for one oscillation. So if I'm looking at my graph of, say, current versus time, it looks like this. the time for one oscillation, say from here out to here, is going to be that frequency. It looks like it gets smaller with time. It actually should be constant. But the frequency will change. Those oscillations will go on at the same rate as they decay. Let me try to redraw that a little bit better. So now my frequency, or my period rather, goes from here to here. That's one period, but I know that it reaches half the maximum current at 0.011 seconds. And so to find the number of oscillations, I say 0.011 seconds divided by the period, 8.7 times 10 to the minus 4. And I get 12.6. So it's sort of midway between 12 and 13 oscillations. You can count them out. 1, 2, 3, 4, 5, 6, 7, all the way down to 12, between 12 and 13, halfway between 12 and 13. All right? So that would be the number of oscillations that you get to the half the current, or excuse me, half the charge on the capacitor. Now also part of the problem, and you'll certainly need to do this, is to sketch a plot of U versus T. Now I've plotted current versus time, but you could also imagine this as being the energy versus time as well. And notice that it's just a cosine function, because that's part of our solution. Right, I have this cosine function right here, but it also has this exponential decay function, which we've seen before, and that exponential decay function you can see like that, where it's sort of overlaid. Like you still have your cosine function occurring, so you have oscillations back and forth, but then you have this exponential decay curve imposed upon it. Okay? I know some of this is probably new to y'all, right? Is this new, sort of? Yeah? Look at the homework. Like, make sure that you can do the homework. It's going to be very similar to these problems that we've done, so you shouldn't have any issues with the homework. But look very closely at the homework. Your test problems will look a lot like that. Okay, and we'll also look at the equation sheets, because it has all the solutions to these differential equations, but make sure that you're familiar with them and that you're able to apply them. All right, let me, and we got 806. We're going to skip over alternating current completely. And phasors. So that is these three circuits. You're not going to see those at all. So down through page 202. And actually, you know what? I think that we've already seen transformers a little bit. I think we can probably just leave off transformers altogether. Y'all okay with that? Would y'all rather do that? Leave off transformers? What would you rather do? Want to do transformers or not? No. Okay. Well, I think we'll just stop there then, and that'll be the end of the material. We'll just leave off those pages after page 195. But let me go through the homework with you and just sort of show you, mark out the questions that you're not going to have on the test. All right, so you'll have this stuff. You'll have that. That's your LC circuit. You'll have this. That's your LR circuit. Okay, you're not going to have this. Anytime number 8, you won't see that. You're not going to have phasers. That's what this is. It's sort of a different mathematical tool that we use for AC electricity. It's unfortunate we don't get to it. We just don't really have time for it. We're also not going to have 11. Oh shoot. You're not going to have 12 either. It's an RLC circuit. Let's go back though. You're not going to have 9 either. That's a forced oscillator. Okay, yeah, so you'll see like number 7 here, but also that's an RLC circuit, but also make sure that you look at the examples in the class that we've done, like the one that we just did for the RLC circuit, and for the other circuits as well. Now they're very similar to these homework problems, but just make sure you look at those, the examples that we did for the RL, the LC, and the RLC circuits. Okay, so we got 8, 9, 10, 11, and 12. You can just not worry about it all. Just don't bother with those questions at all. If you're looking at old tests, well, I think let's just look at the old test in the back of the book. Like for example, you can get rid of that one. This is, I don't know what page this is on, but it's the last exam. Number 13. Number 14 is good. It's a LR circuit. Number 15 is good. 16. Oh, did I not have any of the... Maybe I did that as take home. Yeah, I guess I didn't get to those last year either. Oh, that's unfortunate. AC circuits. Okay. Y'all see what so on this old test, but if you go back further, you can, on this old test, you can just leave off the transformer. Yeah. Okay, guys? On Friday, we'll do review stuff. So y'all take a look at it between now and then and just see where it is that you're weakest. And we can focus on those areas. Don't forget to go back and look at Chapter 5. We have some sort of funky stuff back in Chapter 5. But Chapter 6 and 7 are probably the hardest of them. Oh, Chapter 5 is not easy either. But take a look at Chapter 6 and 7 between now and next class period. And we'll spend some time sort of focusing on your difficult areas. All right, guys? I know it seems overwhelming, but focus on the homework and focus on the examples, because if you can do those, you should be pretty good for the exam. Students tend to do pretty well in this exam, but just make sure you focus on the homework and focus on the examples. Are you hearing what I'm saying? What are you going to do? I think that's what you said. Homework and examples, okay? Y'all have a great day. I'll see you on Friday.